So now we come back to look at current in a series resistance circuit. So the current is the same through all points in a series circuit. So as you're doing your analysis and understanding how to use Ohm's law, how to use the power law, and later how we're going to use Kirchhoff's law, to remember that in a series circuit, the current is the same through all points, through all resistors. The current through each resistor in a series circuit is the same as the current through all the other resistors that are in series. So if we take a look at the schematic and the actual little portrayal here of a circuit, we can see we've got a battery, we've got three resistors connected in series across that battery, and you can see that the current is depicted as I, and I. We could further break this down and call this I total at this point, I total at this point, I total at this point, and I total at this point. So if we look at the resistors then in this circuit, we've got the schematic diagram. All of the resistors are the same 2.2 k ohms. The current is the same through each of the resistors. At any point in the circuit, the current into that point must equal the current out of that point. Okay, notice that the current out of each resistor must equal the current into each resistor, because there is no place where part of the current can branch off and go somewhere else. So keep that in mind. Keep that statement in mind, because when we change gears and we move away from series into parallel and later into series parallel, that statement will only apply in the series branch of any circuit. So therefore, the current in each section of the circuit is the same as the current in all other sections. And so you can see here again in the depiction of the actual circuit, we've opened up the circuit, and between each of the connections, we're going to call these nodes. At each of these nodes, you'll notice the current is the same, 1.82 milliamps flowing through these 2.2 k ohm resistors. So let's look at this in terms of applications of Ohm's law. 1, let's just read through these. Current through one of the resistors in series is the same as the current through each of the other resistors, and it is the total current, I sub t. 2, if you know the total voltage and the total resistance, you can determine the total current by using Ohm's law. I total is equal to V total, the source total, divided by the total of the resistance. 3, if you know the voltage drop across one of the series resistors, you can determine the current by using the relationship I is equal to V sub R, that's the voltage drop across a given resistor, divided by the value of that resistor. 4, if you know the total current, you can find the voltage drop across any of the series resistors using the product relationship V is equal to I total times R. And lastly, the polarity of a voltage drop across a resistor is positive at the end of the resistor that's closest to the positive terminal of the voltage source. So you stick with the convention. 6, the current through a resistor is in a direction from the negative end of the resistor to the positive end. And 7, an open in a series circuit prevents current, and therefore there is zero voltage drop across each resistor. The voltage total appears across the points between which there is an open. So become familiar with these statements. Again, copy them down in your notebook you should be keeping, because you may need to refer to these rules in helping you solve for the analysis of any circuit. So if we look at this circuit, we've got a 5 resistor series circuit, a 25 volt source. We've got four different resistors, each with a different value, 120 ohms, or 820 ohms, 220 ohms, 150 ohms, and 100 ohms. So in looking at the analysis on it, the first thing we can determine is, as far as this source is concerned, it sees one resistor, and that one resistor is R sub T, the total. So let's calculate R sub T. R sub T, then, the total resistance is the value of R1 plus the value of R2 plus the ohmic value of R3 plus the ohmic value of R4. And when we total those, we get a total resistance of 1.29 k ohms. Next, then, we can use Ohm's law to calculate the current. Because notice the current isn't given here. We're given the source. We now have calculated the total resistance. Now that we have the total resistance, we can put the values back into the quotient, V source divided by R total, 25 divided by 1.29 k ohms, and we get a total, once we adjust for metrics, 19.4 milliamps of current. Okay, this is where V source is the total voltage applied to the circuit, and I is the total circuit. So if we go back to our rules, we know that each resistor will have 19.4 milliamps of current flowing through it. Okay, now another example. The current in the circuit is 1 milliamp. So now in this one, we're not given the source voltage, we're given the value of the current. For this amount of current, then, solve for the voltage source. So again, the first thing we have to determine, since we know the current through every one of those resistors is going to be the same, is we're going to solve for the total resistance. So R1, R2, R3, and R4 are summed together, and we end up with 9.5 k ohms of resistance. Now we can take that value for R sub T, multiply it times the value of total current given to us, 1 milliamp, and we have a source of 9.5 volts. So that's the voltage applied to the circuit. So now in this one, let's look at it. Again, we're given another circuit. We're given a 1 milliamp current. We've got three resistors here, 1, 2, and 3, each with its specified values, 1K, 3.3K, 4.7K ohms of resistance. Calculate the voltage across each resistor and find the value of V sub S. To what maximum value can V sub S be raised if the current then is to be limited to 5 milliamps? So we got a two-part problem here. So what we need to do is determine, in essence, what we would do if we put a meter on each of those resistors and calculated the voltage drop. So we're going to calculate the voltage drop for each one of these resistors. So on the first one, the voltage drop V1 is equal to the total current times the value of the resistor, and we get a 1 volt drop. We do the same thing for V2. I times R2 gives us a 3.3 volt drop. R3, I times R3 gives us a 4.7 volt drop. So now what we can do is we can start putting this together. First thing again is let's go back and calculate our total value for the RT. So 1K plus 3.3K plus 4.7K, since these are all in K ohms, we can add them together very quickly, and we end up with 9 K ohms of resistance. Okay. Now, the source voltage then is equal to that total resistance, 9 K ohms, times 1 milliamp of current, which gives us a 9 volt source. So like your 9 volt battery. Okay. So now notice, if you add the voltage drops of the resistors, they total 9 volts, which is the same as the source voltage. So you go back and check it. 1 volt plus 3.3 plus 4.7. When they're all totaled up, same 9 volts. Okay. So now the other part of the a question asks, the source can be increased to a value of 5 milliamps. Calculate the maximum value that the source can be now given that we have up the current to 5 milliamps. So instead of multiplying times 1 milliamp, we multiply times 5 milliamps. So 5 milliamps times 9 k ohms gives us 45 volts. So this is the maximum value that Vs can be raised to if the current is limited to 5 milliamps. Okay, remember, in every case where you have a related problem, I want you to pull out your notebook and solve the related problem. Practice, practice, practice. Okay, let's look at one more here. Series connections often involve using a resistance to limit current to some level. So how can we do that? Well, it depends on how we set up the components in the circuit. In this circuit, we've got a 5-volt source, we've got an adjustable resistor, R1, we've got a fixed resistor, R2, and we've got a little LED bulb. Okay, so if you haven't seen this before, it looks like a diode, a light emitting diodes, and with the arrows is telling you it's a light bulb. So it's a light source. For example, it's necessary to limit current to an LED to prevent the LED from burning out. Okay, you pump too much current through an LED, you're going to burn it up. Okay, so in this case, a red LED is used as an indicator as part of a more complicated circuit. The rheostat, that's R1, that's your adjustable resistor. The rheostat is included to dim the LED depending on ambient conditions. Okay, so those are normal conditions. We'll focus on the two current limiting resistors, so R1 and R2. A red LED will always have a voltage across it of about 1.7 volts when it's on and working within normal operating range. So we're going to learn more later in your courses why that 1.7 is chosen. The remaining voltage from the power supply will be across the two resistors. So in this case, we know we've got 5 volts at the source, and we've got a voltage drop of 1.7, which is characteristic of an LED, being dropped across that LED. So what's left in the circuit when you calculate the drop will be across R1 and R2. Together, the rheostat and the fixed resistors then will have a total of 3.3 volts across them. So that's what's left over. Assume you want the LED to range from a minimum of 2.5 milliamps when the light is dim to a maximum of 10 milliamps bright. Okay, so we're talking about 10 thousandths of an amp. Very small current. What values of R1 and R2 would you choose to accommodate this? Okay, so let's start with the brightest condition when the resistance of the rheostat is adjusted for 0 ohms. So no resistance. It's a pass-through. It's a wire. So in this case, there will be no voltage drop across R1, and 3.3 volts will be the total drop across R2. Okay. Because it's a series circuit, the same current is in R2 as the LED. So we can use Ohm's law to calculate the resistance for R2, V over I. So 3.3 was the voltage drop, 10 milliamps was the maximum current. That we now have a value of 330 ohms for the fixed resistance. So we know that one's not going to change. R1 will change as we adjust it. So now determine the total resistance required to limit the current to 2.5 milliamps. The total resistance is R total is equal to R1 plus R2, and the voltage drop is still 3.3 volts total. So our total then is equal to the voltage drop, 3.3 volts, and the current now is the specified 2.5 milliamps. So our total is 1.32 k ohms between the two resistors. To find R1, then we subtract the value of R2 from the total resistance. So R1 is equal to R total minus the value of R2. So the total we just calculated, 1.32 k ohms, we subtract the fixed resistive value, 330 ohms, and we get 990 ohms. Okay, so you would choose a 1K ohm rheostat, because that's close to 990, as the nearest standard value. You're not going to find a 990 K ohm or 990 ohm, 9/10 of a K ohm resistor in the bench stock. Okay, so we've looked at current. In the next step, we're going to look at voltage sources in series and applying Ohm's law and doing the same types of calculations.